with more than 40 publications in the IEEE Scopus SCI Index journals, and also with several conferences, papers, and book chapters. She has authored 9 national and 2 international books and holds 5 patents and 1 copyright to her credit. She has also organized several national and international conferences and webinars, and plays an active role in NAC SSR preparation and institutional outreach activities. For today's session, Dr. Bansal will be delivering an expert talk on quantum teleportation. Once again, we welcome you, Dr. Pal, ma'am. And now we request you to kindly take over the session. Ma'am, please.
Thank you very much, ma'am. Hopefully, am I clearly audible?
Yes, ma'am, very clear.
First of all, thank you very much and namaskar to everyone. I am very much grateful to the entire organizing team of this ATAL FDP from the Vidyavatani Engineering College. A special thanks for Shrestha madam who approached me for this talk, and heartfelt thanks for Trapti madam for introducing me so well. Thank you, madam. Without taking much more time, I am just going to share my presentation. Let me know whether it is clearly visible or not. Huh?
Yes, yes.
Just a minute, madam.
Yes, yes.
Madam, now my screen is visible?
Yes, ma'am. Screen is visible, but if it is not.
Yeah. Just a minute.
Yeah. Screen is visible.
I'm not in get out the presenting window.
Ma'am, share. Are you getting option? Ashish sir, please.
Madam, I have turned on the sharing option. When I'm sharing the entire screen now, my presentation will getting off suddenly.
Ma'am, don't share the entire screen. What you can do is you first make your presentation full screen.
Yeah.
And then come back to team and over there share window.
Yeah, right side most corner up arrow, na?
Yeah, share window and then select your presentation screen. That will be a better idea.
Sir, I am doing the same process. Okay, by window. Now it is okay. Probably it is visible now.
No, ma'am.
Yes, it is visible now. You can just make it full screen.
Yes.
Yeah, just a minute. Is it clearly visible, madam?
It is visible, but it is not full screen.
Sir, from my end, I put it on the full screen mode.
Yeah, now it is there. Yeah, now it is there.
Visible, madam. It's full screen visible.
Yes.
Maybe a lag due to the network.
Probably, na? Now it is done?
Done.
Okay. Thank you very much, dear organizing team, sir and madam, and all the dear participants especially, because for making successful of any of the event, the active participation of the participants is most important. So without taking much more time, as you all know, from the last 5 days you are attending the sessions on the respective title that they have produced related to the quantum. Nowadays, quantum is a very important area of the research in which the fundamental research on a very small particles are going on. What is quantum? I know that probably all of you are now very much friendly with the term of quantum. If we are trying to get a study of the smallest particle, how they can move, what is the velocity, what is the intensity of light, what they are moving, how we can get the results, how we can transfer the information from the one end to the another end. If we are doing such kind of study for that small particle, that under the overall area, it all comes into the area of quantum only. And what does happen when we are talking about the quantum intelligence? If the small particles, those are moving with the velocity of light or more than this, and we are applying the artificial intelligence, computing techniques and all the related new advanced and thrust technologies with such type of areas, now they become a good research for the upcoming nation. So the title is very well suggested, that is quantum intelligence. By the help of this, we are trying to explore the convergence of the quantum computing in the area of artificial intelligence. As we all know, the artificial intelligence is the area. Means we can say that nowadays it is the technique which can be applied any of the field. Only the condition is one, we have that data, entire data we should know. First we have to extract that valuable data, and then we can apply the AI on the same data. So the field is towards, I'm just trying best of mine to give this talk on the topic of quantum teleportation. So these are the contents that I'm trying to cover in entire of my session. First is the introduction to the quantum teleportation. Now the fiction versus the quantum reality. What is exactly happens when we are going to the study of the fiction versus the quantum reality. Now the basic fundamentals, how the quantum teleportation getting processed, qubits, superposition, how we can send the information of quantum particles as they are very small, so it is important. Now the measurement of non-cloning theorem, quantum entanglement, Bell states, EPR paradox, quantum teleportation protocols, Elias-Bob models, role of classical communication, and the quantum gates used. So these are the few topics that I'll try my best to cover in a best of my knowledge. So first, what is basically quantum teleportation? Probably you all are aware with the quantum physics, quantum mechanics, but the teleportation is a new word for most of the generation. What is exactly teleportation? Before going into the detail, first I would like to describe the word teleportation. Probably you all have heard the word telepathy. What is the process of telepathy? When I am here and somebody is very far from me, and by the process of telepathy we can send the signals, they can get the signals, means just it is the transfer of the information. That is known as the telepathy. Similarly, if we are talking about the particles, then sending particles for a long distance, trying to send the information, getting information via these small particles with the help of any of the process, this entire process is known as the quantum teleportation. So if we are talking about the technical world, we can state like that the quantum teleportation is the process by which the quantum state of a simple small particle can be transferred from one location to the other location. But what is the most important task in this? There is no physical movement of these small particles. So what we are doing? We are just sending the information from one place to the another place, but the particles are not moving in a physical sense. So this is the overall process of the quantum teleportation. For example, it is a key protocol in the quantum information science. Means if we are talking about the quantum physics, quantum mechanics, that all based on the small particles to whom the world is surrounding, steady velocity, intensity, energy, losses, that all we are trying to get steady. So now, teleportation in the popular culture. What is it? Transportation is commonly shown in the science fiction as instant human transport. The best example I can give you, we ordered daily routine things from the Blinkit, we ordered food from Zomato, and nowadays we are using such type of applications frequently. What is happening if we are using such type of application? Our app is developed for keeping continue the instruction. A particular channel is there. We have to search, then we have to go the order window, then online we are ordering payment, everything. This is happening in a queue sequence. Similarly, in the transportation shown in the science fiction as an instant human transport. So the real quantum teleportation is very different and follows some strict physical laws, because if any of the particle is traveling from here to there, some energy must be travel and the energy must be change its form itself. Now, very important, what is science and what is science fiction, and what is the difference between science and science fiction? We all know what is science, and if we talk about the science fiction, it shows the matter teleportation. Before this, we are talking about the particle teleportation, but this time we are talking about the matter teleportation. So quantum teleportation transfers only information. Matter and energy do not travel faster than light. Make it very clear in your mind, if we are trying to send any matter or energy, because they have much higher mass rather than a single electron or single particle. So a single particle, for example, any electron can move with the velocity of light much faster than the matter or energy. As we all know, the speed of the light is very good for traveling for any of the particle. Next is, what is actually teleported? If we are talking about in imagination, what we are thinking, like one place is there as a transmitter, some place is there as a transmitter, and we are just trying to send the signals. But what exactly happening there, that have to be keep in the mind before going to the final setup. Only the quantum state of the particle is teleported. If we are talking about the physical particle remains at its original location and the original state is destroyed. I had just given you one example of Blinkit. If you are ordering anything to Blinkit, is the owner is coming to deliver, or some set of channel is going to be process your order? Similarly, when we want to transfer any information from this place to that place, in that cases, the original place remains same. The particle must stay there only. The physical particle remains on the original location. So the particle is not moving, rather than moving of the particle, the information is moving from the one place to the another place. Now, importance. If we are doing any kind of work, if we are reading, if we are studying, if we are going on the research, whatever we are doing, it must that we should know the importance of the area in which we are talking about. So, what is the importance of the quantum teleportation? The quantum teleportation is essential for quantum communication. Now, the same word is coming again, communication. Let me explain you how the particle can talk. if I'm talking about the human communication, it is very easy and having various ways to exchange our information. Simply a live example we can see here. You all are sitting on your own places. I am sitting here at my place. I am just transferring my energy to you, and you all are getting my energy in other sense. So this is a communication between two parties. Similarly, if we are talking about the communication of quantum, means particle, then different type of processes we have to adapt. The quantum communication is one of the process by which the quantum teleportation must happen. So quantum communication, quantum computing, probably that word you must heard. Quantum communication or quantum computing, both are the very much thirst areas nowadays, and the development of the quantum interest too. And if we talk about the quantum mechanics, then the means you can understand this in a such a way. Quantum science and quantum technology is the main hub. From that, different areas or branches are going on. First one is quantum mechanics, second one is the material sciences, third one is the quantum computing, and fourth one is the quantum communication. So the further sub research areas dividing into the four areas. These four areas is also working in the phase or work of the quantum only. Different of processes we are adopting to understand them. If we are talking about the quantum mechanics, then the superposition and entanglements. If we are talk about the quantum computing, then this case superposition based on the computing techniques and different type of computer algorithms. If we are talking about the material sciences, then the semiconductors and the quantum dots must be there. And most importantly, if we are talking about the quantum communication, then quantum key distribution and entanglement based communication both must be there. So, from where it concept came? So, the quantum teleportation was proposed in the year of 1993 by the great scientist Charles Babbage. And few of the collaborators are there of the scientists. They are working in the same domain from last 7 to 9 years. Finally, after a lot of work done, they have got some results and launched the system. And finally, the first experimental demonstration was done in the year of 1997 after a long time. Now, the classical information. What is the classical information? You can see one figure down of my line. Here, one ball type structure is there. 1, 0, 1 is denoted. The 0 is denoted by the red color circle and 1 is denoted by the blue color circle. Now, the superposition and rest of the probability. If we are sending 0, this probability is going on. If we are sending 1, this probability is there, and overall signal is this. Now, the classical information is represented using bits. We all understand probably what are the bits. Bits are the smallest unit of measurement or the information secured. By bit, we can transmit the information bit by bit in the form of 0 and 1. If I am sending 1 0, then my data length is 1 bit. If I am sending 2 zeros with 2 simultaneous ones, now then my total bits are 4. So what is the bits? They are the smallest unit. They contain only one information at a time, either 1 or 0. That is a simple information. Now, if we talk about the quantum, probably if the quantum word is there, then some mathematical terms must be there, because when we are talking about a single particle, then related to that particle. If the particle is here in the space, some velocity, 3D structure, some angles, some longitude, latitude, all things must be already be there in this. If I am talking about the angle theta, if I am talking about the psi, alpha, beta, cos of psi by 2, this is all the mathematical theory by which we have to be gone through before sending any of the signal from here to there. So if I'm talking about the quantum information is represented using the qubits. The quantum information is represented using the qubits. A qubit can exist in a superposition of the state, unlike the classical bits. From the last 5, 6, 7 slides, we are continuously hearing the word superposition, superposition. So this is the time first when we know about the superposition, how it happened. If I am talking about the superposition, you must focus right side figure once. If you heard the law of EM waves, electromagnetic waves, if I am talking about the 3D structure, this is my x-axis, this is my y-axis, and third one is my z-axis. So electric energy is coming from there, magnetic is in the y-axis, and z is the direction of electronic EM wave propagation. Similarly, a wave that looks like sine wave or cos wave, we can say that if such type of waves are moving and traveling in the air, these all waves are combinedly known as the electromagnetic waves. So what? Superposition allows a quantum system to exit a multiple state simultaneously until the measurement is performed. Horizontal filters, design filters, vertical filters, many types of filters we have to apply on this system. So the superposition is the only, we can say the technology, we can say it a system, we can say it is a procedure, allow a quantum system to exit the multiple state simultaneously until the measurement is performed. The measurement in the quantum mechanics. Measurement, what is measurement and what is the need of measurement? Actually, what is happening? When we are sending any information from source to destination, just assume when we are a day-to-day life example, probably you may laugh. If we are going to the market and we want to buy some vegetables, then we should know how much amount we want to buy, 1 kg, 2 kg, 3 kg. So measurement is compulsory in that case. So the similar case is here. If we want to transmit some energy from one place to the another place, at the same time, this is very much important. You should know what is the quantity you want to send from one place to another. Similarly, at the same time, what are the possible states nearby who surrounded the entire area and the favorable conditions so that your entire information can be transmitted without any of the losses. So measurement collapse the quantum state into a definite values and destroy the superposition, right? If we are talking about the collision, what is collision collision? If one wave is there, one particle is there, and the particle is moving like that, in that case the system get collapsed with the other system and the other criteria. So this all be processed before itself while we are transmitting the signal from one place to another. Quantum states. A quantum state describes all information about a quantum system and it represented using direct notation that is known as psi. Psi and r. These are two important symbols that or notations we are using in the entire quantum system for notation of different type of mathematical expressions. if I'm talking about the basic functions that we have to know for this quantum teleportation, that is psi1 psi2, the formula is psi1 divided by psi2 is equals to the integration of minus infinity to infinity psi1 multiplied by psi2, and these are the vectors values we can represent for the different equations. So the direct notation simplifies the quantum calculation using the function that is called bra and ket symbols. Now, very important is the no cloning theorem. If I am talking about the no cloning theorem, what is this no cloning theorem? It states that an unknown quantum state cannot be copied perfectly. What does it mean? If we are talking about the clone, what a clone can do, just imagine in a simple, forget about the quantum, forget about any engineering background, as a normal human being, just to try to imagine what first comes into your mind when you heard the word cloning. When we heard the word cloning, we can assume some clone is there, means some two similar structure, one is original, one is duplicate, but that duplicate can also work like as original, it also have the same characteristic like as original, that is combinedly known as clone. So when we are talking about the cloning theorem, it states that an unknown quantum state cannot be copied because it is not a 2D structure, it is not a hardware setup, it is all about the energy and information transmit that is going to be happen in the space. So what is happening here? We are using for teletransportation. First we have to calculate the parameters, that is psi, delta, bra, ket, and must application of known cloning theorem. Now the significance of the no cloning. What is the significance of no cloning? So the potential security, vulnerability causes are there because the quantum states cannot be copied ever. Ever we cannot copy the quantum states. Teleportation becomes the only methods to the quantum information. If we can think about that, we can transmit the information with any other method, but it is not possible. So what a no cloning theorem can state, it is impossible to create an identical independent copy of any arbitrary unknown quantum. If you want to make a robot of pile, then you can make, but if you want to make any structure that is very similar of any of the quantum energy, that is unlikely, impossible. So that is can be proven by that theorem. Now the important term is quantum entanglement. What is the quantum entanglement? That is a phenomena where two particles share the single quantum states. For example, me and my friend went to the restaurant and we ordered one plate pasta, for example, and we are sharing that same plate. So similarly, the quantum entanglement is a phenomena where two particles, means one particle is here and second particle is here, they are sharing a single quantum state ever when separated by a large distance. In my first figure, you can see the figure. One particle is there that seems to be big in the size, and one particle is very far from that particle. It is seems like as a small, but the particle size is same because that is too far seems like be small and that is near seems like be big. You can see one connected line between these two particles. So what is it that this is the line that connects between 2 points. Fine, when separated by the large distance. Now in my second figure, you can imagine what is this? My second figure is representing there are two girl and boy. They are in the thinking state. What is happening here in this figure? They are thinking simply if they both are using the first object as a trial state, they cannot share it. But that can be possible in the states of quantum. Now, if I am talking about the properties of entanglement, that is very important that we should know what kind of properties. The very important properties can be defined like discord and accord. The entanglement particles show the strong correlation that cannot be explained by the classical physics. Very important is Einstein's law. Einstein's view, sorry, not law. The great scientist Albert Einstein referred to entanglement as spooky action at a distance. What is that spooky action at a distance? And question it's on a physical meaning. If we are in the physical meaning state, means we have to know the spooky action at a distance, what can become, what type of rays are coming, how we can control, what type of information we can collect and recollect. Such type of all data we should know when we are trying to do it. So that is achieved and done by the great scientist, that is Albert Einstein. Now, the next one is EPR paradox. What is EPR paradox? The EPR paradox highlighted the strange nature of the quantum and the quantum entanglement and challenged are the completeness of the quantum mechanics. If I am talking about the 2D structures, so when we saw a picture, only y directional and x direction is there. But if we are talking about a particle cannot be having only two states, it must have three states only. So these all three states can be defined by the different parameters to explain the completeness of the quantum mechanics. Maybe sometimes lot of challenges are there, lot of involvement of the means unwanted particles like clashes, collision, collapsion must be there, but we should know how to reduce, how to handle, how to apply these required theorems. Now the Bell states. If I am talking about the Bell states are maximally entanglement two qubit states and are used as the quantum channel in the teleportation. So I just introduced one equation or figure sort of for you as an example. If we are talking about, we want to send some information and the relative data related to this, then we can send this to the entire system like as x minus x 0 in between of parameter. In that we are considering just as bits. They are considering or carrying some information with each bit. They all are known as the Bell states. Means in simple words we can understand like that the states, they can explain the exact location and the situation of any of the particle by which we can mathematically derive it in such a way so that teleportation can be happen. This is known as the Bell states. Bell states examples. One Bell state is the psi plus is equals to plus modulus of 11 is divided by under root 2. What is this? You can see in the figure that one dark black dot is there and one standing line is coming out from that black dot and it is joining from the same space. The H is there. So one Bell state is psi and which shows the perfect correlation between the two qubits. if there are 2 qubits and we are just trying to do the Bell states, in that case they have to be like that so that they are perfectly correlation between these two. Now the role of the entanglement. Entanglement enables the transfer of quantum information without the physical transmission of the particles. This is the light source from where the light is coming. Initially in between lot of particles are moving like that, the energy are moving from that side and that is moving from the different side. So this all has happened due to this entanglement that is enables the entire quantum information without the physical transmission of the particle. You can understand this by a simple example. When many of the signals, when we are listening the FM signals, 93.93 FM, 95, 98, many of the frequencies are there on which the songs has already broadcasted in the air. When we are trying to get tune into our channel, then only we are able to listen that music. So what is happening? Is there any person lively song is possible? They are going that place and singing the song for us. No, that is not happening. Actually, what is happening? They have already sent their own data by some encoding, decoding in the air, and they all get this entire information with this system. Now, the teleportation participants. The protocol involves two parties, one is Alice and second one is Bob. In simple terms, we can understand like that, one is the transmitter and second one is the receiver. So what Alice is the transmitter, and what is Bob? Bob is the receiver. Means when Alice is sending any information, Bob is there to receive it. When Bob is sending any information, then Alice is here to receive that information. We are just representing it. Alice is a girl, Bob is a boy. They both have some data of particles or quantums. They both are sending the data. Some watch clock you can see here that is showing at what time you are sending your data to that information probably. So what is this? This is all about the overall interaction or the system how which we are sending our data from one end to the another end. Now the next one is very important, that is resource. If we are talking about the resources, what is happening? Actually, resources are what? We are just assuming that we are transferring the data, we are sending the signals, but it is not possible always that all resources are available at that time, at that instant, without any distortion, noise and signal to noise. Means many of the obstacles must be possible there if we are talking about that system. So the quantum teleportation requires an unknown qubit, an entanglement pair and a classical communication channel. By this channel, at least they can transmit the energy of that quantum. So the measured outcome is shared between the Bob. We just talked in the previous slide, we explained what is Bob, what is Alice. Alice is sender, Bob is the receiver. We are just trying to send the information from Alice to Bob and the vice versa from Bob to Alice, and the local measurement of the qubit A, qubit B, center of the quadrant. So you can see the qubit C is activated and the lot of signal by the different communication channels we are sending throughout the system. So this is all happening just because of the required resource. Now, if we talk about what are the possible required resources, possible required resources for any of the teleportation process, we can explain it like that. Heavily, whether when you are means, let imagine if the weather is not clear and you are trying to send that energy into the space. So what will happen? The quantum information teleportation or the hypothetical science fiction concepts of matter. So it is very important if we are talking about such type of systems. Now, what is happening? What is happening in the case of if we would be need for like want to know what are the basic. So it is most important and required an entanglement quantum state to be created for the qubit, and that has to be transmitted. So these are the system we need to require. In simple words, we can understand like that. It is the structure of 3 qubits. First, Alice puts her qubit into a quantum superposition using what is known as a handmade gate, and then she interrogate her qubit with the Bob's qubit using what is called the controlled unit. So basically 3 qubits are required here for that entire session. Now, if I'm talking about that the year by year, right now, if I wish to teleport it, teleportation of any of the quantum, is it possible? So, right now, scientists have achieved a quantum teleportation. By the help of this, we can send some matter teleportation also, but physical objects are to be needed in the near of space criteria. So what is the initial setup that we have to require? If we required and set the Alice possesses the unknown qubit and the one entanglement qubit, while the Bob holds the other entanglement of the qubit. So this is the basic structure. First, now how it happened? We should know the steps, basic steps, how it is happening, why it is happening, when it is happening, and while during the entire process, what kind of challenges can be come. So, step 1 is entanglement sharing. As we can understand by the title itself, sharing. If we are sharing something between two parties, that is simply there is no science behind it. I am just talking about of word sharing, not entanglement sharing, word sharing. If I am talking about the word sharing, then we must know that we wish to simple transfer of information vice versa between two bodies. That is called the sharing. For example, we are teaching to our kids, beta, please share, do share. So what is happening in this world? Sharing the information, sharing the energy, sharing the objects, sharing the resources means if we are using any of the resources on a sharing basis, if we are using any of the objects, sometimes you need it, sometimes me need it. So the same is happening in the step word itself. Alice and Bob both share an entanglement qubit pair before the teleportation begins. Now the second one, step 2 is the Bell measurement. Alice performs a Bell state measurement on her qubits, destroying the original quantum states. So the qubit 1 is different and qubit T is different. As you can see in the figure itself, in qubit 1 is what is happening, in qubit 2 what is happening. If it permits, sign permits, then what is the multiple data is continuously sending from the qubit 1 and similarly at the same time from the qubit 2, but some bit splitters are there. What they are doing, these bit splitters are used to divide the way of entire system by the help of beam splitters. You know the word beam splitters. Beam are the light waves. They are coming from the qubit 1, qubit 2 and qubit 3. We are assuming that meanwhile during the teleportation, or we can say the normal process, they mixed with each other. What happened? We have to be segregate them. So with the help of beam splitters, we just segregated all the systems. So Alice performs a Bell state measurement on her qubit. Who is Alice? In my example, I showed to you Alice is a girl, or we can say the sender. Alice performs a Bell state measurement on her qubits, destroying the original quantum states too. So the measurement outcome. What is the measurement outcome? The Bell measurement produces two classical bits of information. Classical communication. Alice sends two classical bits to Bob using a conventional communication of channel. So one channel is receiver, one channel is skin, air, fat and muscle. So here you can see receiver, source node are two nodes. One is house. From there the signal is coming to the receiver. From the source signal is coming to the receiver. There is a network using the conventional communication system we have set up over there. Similarly, in the rightmost picture, you can see like some stomach, muscle, fat, skin, air, and all signals are coming through the receiver. So the independence, discontinuity reflections the various things. So the role of the classical channel. Exactly, what is the role of the classical channel? The classical channel ensures that the teleportation does not violate the speed of light. We cannot think like that any signal, any quantum particle or anything can be moved in the space beyond the speed of light, because the speed of light is the maximum velocity by which any particle can move. What is this? We know that. What is the speed of light? 3 × 10⁸ meter per second. Now, what is the Bob's operation? What is the Bob's operation? Bob applies a quantum operation based on the received classical information too. So when we are talking about the Bob applies a quantum operation, what quantum operation he has applied? Whatever he want to apply it. So here is the Alice, here is the Bob. Some signal is coming with we are trying to calculate it. When we are trying to calculate it, both of the signal are in the even worse state. We can split them by the help of beam splitter itself. Now, from the last half an hour or 1 hour, we are talking about the different mathematical operations, different like operators we can use, how it is happening without any of the knowledge of operators. So, what kind of operators a Bob can use? Who is Bob? Bob is just a receiver. So, Bob uses poly X, poly Z gates to reconstruct the quantum states. As we can see in the figure, we are simply using NOT gate. What a NOT gate can do? Simply invert of the input. If we are giving A, then it will convert into A bar. If we are giving B, it will convert into B bar. Simply. So now, what is the issue with that? The issue is we are using poly X gate. So by the help of this poly X gate, what we are doing, if we are giving simple bit 0, so this gate is converting that 0 into 1. If we are giving 1 to that gate, poly X gate, that is converting that 1 into the 0. So what is the truth table of this system? We can understand that 0, 1, 1, 0, simply transpose. Now the final state, recovery. Initially 4-5 slides ago, did the correlation. A successful correlation must be matched with 2 qubits, then only we can process our signal for the further transmission. After a correction, Bob obtains the exact quantum state that Alice accordingly had. The very important statement, till the time what we are doing, till this slide, what we are trying to understand, right? What we are trying to get from last 5-6 slides. One is we represent as a girl named as Alice. Boy is the Bob, worked as a receiver. We named it as a Bob. Initially, they want to send the data, means quantum teleportation, they want to be happen. But initially steps they done. Now at this stage, what is happening? After the perfect correlation, I already told you for transportation, teleportation, the correlation must be matched between two bodies, then only it can happen. So the Bob, if the Bob obtained the exact quantum state that Alice originally had, what is happening? If I am speaking and you are getting my words as it is same, whatever I am speaking, then only it is happening. If what I am speaking and what you are getting, the words are not proper, first case, if the delay is there, if the net connection is slow, many causes may be there. So in this case, the correlation or the correction, both are different. After the data correction, if whatever I am telling, you are getting exactly, then the perfect match and alignment must be there. So the destruction of the original states. Here you can see in the figures, few graphs are there. The original quantum state at Ali's location is destroyed. As I told you earlier, particle cannot move, only the information can move. But after sending the information, the particle place must be destroyed so that we can prevent some duplicate.
Ma'am, you are not audible. Hello.
Not audible to you?
Now it's okay. I think network problem was
Continuously
there.
talk.
No, ma'am. It was only for a few minutes. Now it's okay.
Okay.
Ha.
So, as I already told you, if you want to transmit any of the energy, no particle can move means faster than the light. As we all know, the light particle is having the faster energy, that is the speed of light 3 into 10 to the power 8 meter per second. So if we want any of the quantum teleportation does not allow faster than the light information. Now very important, the quantum circuit. Till the time we are talking about how we can transmit, why we are transmitting, what type of resources required, what are the challenges, and what is the basic procedure. So before sending any of the data, before sending any of the information of the quantum particle, we must know what type of gates. Till now we are example only one gate. Why not gate? What we are doing? We are just transferring, means changing the states of data. If we are putting 0, then the same time it is getting 1. If we are putting 1, the same time we are getting as 0. So quantum teleportation can be represented using the quantum circuits that involving the Hanmar and C0 gates. Different type of gates, mathematical operations we can use to calculate the data probabilities. So before transmitting of any of the data, some encoders must be there to encode the entire data, and after receiving the data to that place some decoding must be there on the same like node or information, so that at least we can get a what is the exact situation of the transmission. The next one is the experimental teleportation. Quantum teleportation has been demonstrated using the photons, ions and atoms. In the very starting of my presentation, I told you that when we are talking about the single particles, it may be neutron, it may be ion, it may be atom, it may be electron, any photon can be there. It must have some energy mass so that it can move from one place to another place. So this is the basic theory of quantum, so that we can send our data from one place to another place. In this slide, we are just trying to explain with the help of this diagram how the photon teleportation takes place. If we are talking about the photon, we all know what is photon. If I'm trying to explain, the photons are commonly used due to their low interaction with the environment. What is this low interaction? If I'm talking about the low interaction, what is that low interaction? If I'm having less weight and less mass, and other particle having more mass and more energy. Simple example, that particle can move more distance rather than me, because that particle having more energy and more velocity rather than me. So this is the simple criteria. Here two particles we have represented in terms of two bits, like A is 1, second one is B, and some EPR pairs are there, so that we can represent them. So the long distance teleportation are there. Teleportation has been achieved over 100 of kilometers using the optical fibers. I told you in initial in the starting of my presentation, what is the long distance communication can happen, how the long distance communication of particles can happen. The only technique is the quantum teleportation, by which with the help of optical fibers we can send our energy to the hundreds of kilometers. You can see in the upper left diagram there is a picture of optical fiber, how we can send our light energy through this optical fiber. In the rightmost picture, there is a pump laser by which we are transmitting the vertical polarized pump and the horizontal polarized photo for the entanglement photons. So, what is the free space teleportation? Free space teleportation experiments enable the communication without physical cables. One more new concept. In my last slide, what I told you, we can send it through the help of optical fibers. Optical fibers.
2 hours and amount debit ayi నాకు ఇంతవరకు ఇనిషియేషన్ అయినట్టు నాకు నంబర్.
What madam? Are you saying something?
No ma'am, no.
Okay, some voice is there.
Hi, yeah. Wait a minute.
Okay.
We'll do something.
So what I told you in my previous slide, that we can send that information with the help of optical fibers. If we are putting some optical fibers, then we are somehow establishing some hardware setup. Okay, but if we are trying to do the same with the free space teleportation, free space means doesn't require any single cable for transmission of energy from one place to the another. So what is free space teleportation? Experimental enable communication without any physical cable. No optical fiber we are using in that process. Okay. Now the satellite. These all are the examples of quantum teleportation. initially we studied how the teleportation becomes take place. So why we are doing this? What are the advantages and key challenges? Then the free space communication. Now the satellite teleportation is also possible. The the distance exceeds 100 kilometers. Can you imagine it is possible to put the single optical fiber till so long distance? No, because if it will get destroyed or disattached at any of the place, at the same time it will create the cause of loss of energy. So in such kind of information transfer system, we are trying to use the free space communication so that we send our energy from here to there. So this was the first experiment of the Chinas in the field of teleportation when they achieved the maximum distance teleportation over the distance of 1200 kilometers. Now most of the satellite experiments. What are the satellite experiments? The satellite teleportation enables to the globe scale quantum communication network. I told you that quantum is like a simple particle and we are talking about communication. If the communication word is there, then you must understand that that acquires the complete word itself inside it. Word is very simple, that is communication. If I am calling to a person who is sitting in USA this time, that is also communication. If we all are connected with this virtual network, this is also communication. As a teacher, as a student, if we are sitting in a class, that is also a communication. In our families, we are talking to each other, buying things from the market, means everything is communication. Talking to each other is communication. In simple words, if we are trying to exchange the energy of the photons, of the electrons, of the simple particles, quantums, that all communication, they are not able to speak like a human being, but they have that information inside them, that is a second form of world that can be globally stabilized by the help of this experiments. Now, when we are trying to set up any experimental space, when we are trying to do anything, some key challenges but obviously are there. So, what are the key challenges that has to become when we are going through with the teleportation process? So, simply quantum teleportation faces challenges such as noise, decoherences and signal loss. I must elaborate this a bit. What is noise actually? Taking it with a live example, we all are listening music via FM radio. Probably in every state, we are used to listen the song with the help of FM radio. Few fixed channels are there, 95 FM Tadka, 98.3, some 100.4, some 91.3, means on a particular frequency, they already tuned their channels. Exactly what is happening there? They all channels broadcast their information in the space. So once a thought came into my mind, why they not mixed up or means getting destroyed? When they all signal mixed with each other like that, somehow it is very tough to extract the original information from that entire bucket of the information. In that case, then later on after studies, I got to know that was the question that came into my mind 20 years ago, not this time when I was doing my BE. So, how the information can be extracted from the bucket of the knowledge. Then I got to know with the help of encoders, they can protect their signal. After that protection of that signal, they are sending their information to the space. Then again, at the receiver side, some decoding must be happen over there, and the entire things got easily describes or detected what the original information was. So in terms of challenges, what is the noise? If any unwanted signal anyhow mixed in our original information, then what will happen in that case? Our original data get distracted or destroyed. So if we want to protect our energy, our data, our information in terms of any of the attribute, the noise must to be less to make it more efficient. And if I talk about the decoherence and the signal loss is the loss that we are having after the unwanted signals that have entered into the main information. So these 2-3 are the big challenges when we are transferring or any of the quantum teleportation from one place to another place. What is decoherence? So interaction with the environment causes loss of quantum information. Simply, interaction is what? Interaction with the environment. Exactly. When I am speaking anything and talking to you, this is the information exchange between you and me. But the same signal is coming to you via air, then definitely I am interacting with environment also. So the same thing is happening in the case of quantums. This is a process of decoherence in which when the interaction with the environment cause of loss of quantum information. Okay. How we can correct the error? Till that we have studied how, why, what, which setup and till challenges. Key challenges we know. Now the time we can figure out what type of error corrections can be possible with the system. The quantum error correction techniques are required for the reliable teleportation. Have you ever heard for the Huffman coding and other type of correcting techniques? For by the help of such type of techniques, we can correct our data. We can like extract our data in the different criteria as per our choice. So what is happening here? You can see in the figure in middle there are two dots, means two particles are there. In the next step left and right, then are 3, then are 5. So what is happening here? If you can see some like nest is there. From one bubble 3 lines are coming out to the second stage. From the second stage 2 lines are coming out to the first stage. Then again from the every photon the similar type of waves are coming out. What does it mean actually? It is meaning as the different kinds of signals are coming out with the system and we are getting out with the mix up of different kind of information. So these circles are representing such type of signals. So by the different techniques of error correction of coding, we can, there is a subject, entire subject is based on that is the ITC, information theory and coding, which may have the entire details how the error can be detected and how the error can be correct. Both are very important. You can correct the error only in one condition, when you know what is the error, means what is the possible error detection, then only you can correct it, otherwise it is not possible. So application quantum communication. What is application of quantum communication? in which areas we can use these communication, because if we are using anything, if we are not able to implement our research or our knowledge in any of the application, there is no mean of that kind of research. So definitely some specific area applications are there so that we can use quantum communication. So the teleportation enables the secure quantum communication between resistance to the eventropy. Probably you can understand my first figure. There is a key and one side is a lock. Why lock is showing is open. When we are sending the information, that time your information is locked because we already applied and did the encoding on that data. But when we put the key inside that data, like as decoding, then we can extract the data. So that similarly by this side, you can see the green signal, that is of mix up of EM wave, and the part of receiver, the original signal can extracted. Now, the application of the quantum, that was the application of quantum communication. In my earlier slides, I shown you 4 major areas in which the quantum teleportation can be possible. So one I was explained already to you. The second application area is the quantum cryptography. Nowadays, the cryptography is the area in which lot of research is going on. So used in the quantum key distribution for unconditional security. What is this? If we are calling that, what is, first we have to understand what is exactly cryptography is. The cryptography is the science of the practice basically. Means we can understand like that the cryptography is the basic science to secure the communication. You probably you have heard the word cryptocurrency is also one word. So what is the cryptography? It is a secure communication using some mathematical techniques. We should apply some mathematical techniques to transfer the readable data. Means that must be a plain text into the unreadable code. Why I am saying like that? When we are talking, that is the readable data or audible data. For example, I am a person who is from Rajasthan state. Take it a very live example. I am from Rajasthan state and your college is situated, that Vidyavardhini college is situated at the Maharashtra, Mumbai. So probably you people are very fluent in Marathi language, but I am not. So how I can encrypt my data? How you can encrypt your data? While talking to Marathi, you can encrypt your data. Similarly, what is cryptography? You have sent the data in some readable and plain text, but some unreadable codes must be added into that data to ensuring only authorized particles, means authorized persons at the center side like Bob, they can encrypt the data and they can easily understand the situation. If I am talk about the key features of that, that is basically process of encryption and decryption and confidentiality also. Now, for further, the application of the area of quantum computing. If I am talking about the application area of the quantum computing, then I must know support the transfer of the quantum state between the quantum of processors. What is exactly that? Quantum computing is very known word. If we are trying to use any artificial intelligence related application, they all are covered the area of computing basically. For these computing applications, we required some extraordinary GPUs or TPUs to process this data. Normal CPUs are not able to process this entire data exactly. So, in simple terms and in simple language, we can say that the supports transfer of a quantum states between the quantum processors. What are the quantum processors? We can state like, as I just told you, not a simple CPU like GPUs, TPUs of high processors computer systems can be processed that data, that is all comes into the category of quantum computing. What? Now the application area in the field of quantum internet, very important area because that all cannot be happened without internet. You know, internet is the word and it is the world. I used to say that this quote, internet is not a word, internet is world. So quantum teleportation is the backbone of the future quantum networks for any of the technology. Okay. Now the application in the area of space communication. So it provides a secure communication between the satellite and the ground stations. As I already shown you in my previous slide and presentation that the system that was connected with or without setup stations from transmitter to the receiver for the different areas, we can easily build a strong connection between these two. If the signal or information transmitted by that system in terms of energy and photons, it must be encrypted and that must be decrypted at the receiver side. Fine. So, industrial impact. Industrial impact, the quantum technologies will impact us cyber security and the finance and the defense too. These are three major areas in the cyber security, in the finance and the defense, where the industrial impact can come with the help of this quantum. Now, the important is the limitation. With every technique, with every procedure, with every experimental setup, we have to face some key challenges along with some limitations. So, the limitation is, as we all know, optical fibers are too expensive. If we are talking about the quantum particles, the basic experimental setup on the Earth, station, satellites, everything is very costly. So overall, high cost is the most important limitation. Feasible hardware, as I told you, the hardware is also a big challenge to set up such kind of structure, and the environmental sensitivity that can limit the large scale deployment. Now the scalability issues. The scaling of the quantum teleportation to the large network, it is still an open problem. We can still not say that the all scalability issues are till now sorted and 100% data in terms of energy we can retrieve at the receiver station. So we discussed about the work that already have been done in this same area, but some future research are also be there, like as some specific areas in that we can continue this research, like focus on the stable qubits, long distance communication, long distance entanglements, all the integration with the classical system. As I already told you, if you can focus in the first figure, two particles are there with the same mass, same energy, same size, but who is closer to me, that seems in the big size, that is too far for me, so it's looking smaller in the size. there is a connecting line between two particles that can be make a simple connection between two particles. That is a sharing process. So the advancement of the technologies, we can say that advance in the material sciences and the control system can be improve the teleperforming performances for the future uses. So the ethical and the security aspects, we already discussed this point that the quantum teleportation enhances the privacy, but it raises new security also. When we are doing encryption at the transmitter side, but what happen if it will be not decryptive at the receiver side, so it will not fully security considerations. This is the comparison with the classical communication. So that was the classical communication. First, the second one, B figure is the quantum communication, and third one is the entire setup of the classical as well as the quantum communication. We can clearly get that with the figure that quantum communication system is having much higher frequency and accuracy rather than the classical systems. So this is somehow the future scope of this. The quantum teleportation is expected to be revolutionize the global communication system for future. But this is not very easy to work in that area because quantum is the area we hardly get good setups and good like resources to be get good results. This is all about the conclusion of my last 1.5 hour presentation that the quantum teleportation is a real and experimentally verified phenomena and a fundamental technology for the future quantum systems. So thank you very much for patience listening in from last 1.5 hour. And last, I must end my presentation with these words that the quantum teleportation proves that the information not matter defines the limit of the communication. It can be globally. So thank you very much to everyone for this patience listening. Hopefully I am able to deliver few key points somehow. This is all done from my end.
Yes,
Participants,
ma'am.
if you have any queries, you can unmute yourself and ask questions.
Good evening, ma'am. Am I audible?
Yes, sir, you are audible, sir.
Yes, ma'am. My name is Shardul, and I am a lecturer from Gujarat. I work in particularly physics research. So, uh, but the session was very interesting for me as well because I know a little bit of electronics and little bit of quantum, but to merge two concepts and the teleportation and the was very enlightening to say the least.
Thank you so much, sir. I was tried my best entire the session. I was trying I can give you the live examples day to day so that I can connect with you all. Basically, I am from electronics and communication background. I did my BE, MTech, PhD and doing postdoc now in the same domain. But somehow I'm relatively correlate with the physics domain also. So that I was trying to deliver something to you all guys. Sir, Gujarat is
Yes,
very near to Rajasthan. You can be in touch with me.
sure, ma'am, sure. Yes, ma'am. Actually, I am connected to your profile in LinkedIn as well. So,
Oh, that's great. Seems to be great, sir. Thank
uh,
you.
yes, ma'am. Yes, ma'am. I had one. It was not. It is not a doubt, but it was one wondering that how noise is possible in teleportation because one state is destroyed and then another state is created, so there is no scope of मतलब वो स्कोप ही नहीं है एक डिस्ट्रॉय हो रहा है मैम दूसरा कनेक्ट क्रिएट हो रहा है सो देयर इज
Sir,
नो स्कोप ऑफ इंटरेक्शन और
Sir,
entropy.
I may clear it a little bit about this. There is only the scope when from here your signal started. Then this time this is got destroyed. Fine. But
Yes.
when your information is traveling into the space via this reason, probably somehow it can be interact or mingle with the other energy signals. However, my signal is encrypted fully, but somehow due to some weather condition, due to some noise factors, some unwanted signal must be added into my system in such a way that some noise can be influence of my original information. That can be possible in the broadcasting of the signal when any of the communication is going through the space area only. That time it can be happen, sir.
Okay. Thank you, ma'am.
Welcome, sir. Is there any other query or anything?
Yes,
Uh,
participants, any questions?
Tripati ma'am, I hope the session was bit
Was
okay.
very,
Means,
it was very good, ma'am. Session was very good.
thank you.
Um, if no questions, then I will conclude. Ashish sir?
Please go ahead, madam.
Okay. To conclude with, today's session offered a comprehensive and insightful understanding of quantum teleportation and its real-world relevances. Dr. Pal ma'am highlighted how quantum teleportation serves as a fundamental technology to secure quantum communication, advanced quantum computing, and future quantum internet. She clearly distinguished between the science fiction concepts and quantum reality. She highlighted role of classical communication on quantum gates. Also, gave the clarity about the protocols used. She explained how security is provided through no cloning principle, ensuring inherent security in quantum system. She also highlighted that noise like uh, noise signal can provide the challenges and affect the performance of quantum teleportation. Finally, ma'am introduces the real life application area of quantum technologies like including quantum communication, quantum cryptography, quantum computing, quantum internet, and quantum teleportation. Also, she highlighted the future scope of quantum teleportation. Overall, the session was effectively bridged theoretical foundation with practical quantum communication concept, providing clear understanding of quantum teleportation from fundamental to protocol level. So thank you so much, ma'am, for this insightful and enriching session. We truly look forward to interact with you again in the future session. Thank you, ma'am.
Thank you, madam. And I should greet once HOD EXTC. I can see he is also in the meeting. Initially, I have not seen. Thank you very much, sir, for giving this opportunity to join with you virtually. Thank you so much, sir.
Hello,
Yes,
ma'am.
Dr. Amrita Ruperi ma'am is our HOD and Ashish sir, Dr. Ashish sir is there in this session also. So
Okay,
he was
Amrita ma'am.
interacting with you.
Thank you,
Uh,
madam. Thank you for you. Thanks a lot.
Thank you, madam.
And ma'am, this is Shaista. I'm
Oh,
in touch
hello.
with you. Yeah,
Hello,
I'm
Shaista madam.
yeah. So, ma'am, I want to thank you. First of all, I want to tell everyone that ma'am is not well, and I can see the enthusiastic, ma'am. It's like you're not well, so you have given us so nice lecture. Then, if you must be more well, then how better you can
Ma-
give? I can.
Madam, actually, I am in IIT Bhubaneswar from last
Yeah, ma'am.
15 days. I told you, na.
Yeah, ma'am.
Today by 5:30, my all exams get over, and by the grace of God, I got third position in entire AICT QIP program in robotics and AI.
Arey wow,
oh,
very
ma'am,
nice, ma'am.
congratulations, ma'am.
Congratulations.
Congratulations, madam.
Congratulations, ma'am.
Thank,
Congratulations.
Congratulations, ma'am.
thank you,
Congratulations.
thank you. I was in rush to join this session after just a certification. I was in rush to join this session. Na? I had words with Chester, madam.
Yes, ma'am. Thank you so much. Because and I can see like you're so active, ma'am. You are doing so many things. Like great to like see you that you are managing so many things. Like you are reviewer for our sessions or like for our paper also. So many things. So
Yes.
thank you so much, ma'am. Like we are like proudly we can say we have a great person with us. Thank you so much, ma'am. We'll be in touch. Yeah.
Thank you,
Thank
madam.
you, ma'am.
Thank you.
Okay. Thank you,
Okay.
ma'am.
May I leave the session, ma'am?
Yes, yes, madam, you can leave. Thanks
Yes,
a
Yes.
ma'am.
lot.
Thank you.
Take
Thank
care,
you.
ma'am. Take care. Bye.
Hello, Dr. Ruksan, sir. Hello.
Hello everyone. Can you hear me?
Yeah, yes, sir, sir. Sir,
Yes,
this
sir.
is
Yes.
Dr.
Okay.
Amrita Ruperi, Head and Coordinator of this Faculty Development Program. On behalf of
Okay.
Vidyavardhini's College of Engineering and Technology, I welcome you, sir, and thank you very much for accepting our invitation. Now, I request Kanchan Patlikar, madam. She will introduce you to all the participants and then we will start the session. Over to you,
Yes,
Kanchan,
ma'am.
madam.
Yes, ma'am. Good evening to one and all. Welcome to the 10th session of AICT sponsored ATAL Online FDP on quantum intelligence, exploring the convergence of quantum computing and artificial intelligence. I, Kanchan Sarmarkar, Assistant Professor, Department of Electronics and Telecommunication Engineering, VCET, take this opportunity to warmly welcome our next speaker, Dr. Ruksan Al-Haq, who will be delivering a talk on the topic Quantum AI and its applications. Dr. Ruksan Ul-Haq is a quantum scientist turned techpreneur who firmly believes that quantum-based technologies are going to entirely reshape a lots of human enterprises, including research, education, healthcare, agriculture, etc. Dr. Ruksan has more than a decade of research experience across the top-notch research centers and industry, especially in the domain of AI and quantum computing. He has worked with the Forbes 100 organization, including Johnson& Johnson, IBM, Bosch, BP, etc. Currently, he is pushing the boundaries of deep tech innovations with Chinar Quantum AI, which is one of the few quantum AI companies in India. Chinar Quantum AI is also operating in Turkey, Kuwait, and Germany. Sir, we are delighted to have you with us today. I kindly request you, sir, to begin the session. Over to you, sir.
Thank you. Thank you so much. So my teammate Hussein, he will present the slides. Hussein, can you present? Can you
Good
share the
evening,
slide
everyone.
screen?
Good evening, everyone. Am I
Good
Good
evening,
audible?
sir.
evening,
Yeah.
sir.
Yes, yes, you are
Yeah.
Yes.
audible,
Yes.
sir.
Actually, I am trying to present, so it's saying only meeting organizers and presenters. Okay. Thank you. Thank you for
Yeah,
giving
I
me
have made you
access.
presenter, sir. Yeah.
Okay. Yeah. Good. So yeah, first of all, I would like to thank the organizers for reaching out to me and allowing and giving this opportunity to present some of our work. And what I'm going to do is I will be talking about quantum intelligence, which is on the one side, it is the next frontier of quantum computing. And also it interfaces between what are the applications of quantum computing and in the domain of the AI. So the way I will structure my session is I will first of all start from the very foundations of quantum computing. I will talk to you about what is quantum computing and why is it important and what are its foundations. Then we will take it to the domain of the AI. We will try to understand how quantum computing and AI can be brought together and what are its various applications. So first of all, you must be heard of quantum computing as a new technology, as a new important and promising and emerging technology. But the question which we want to ask is how is AI quantum? better or how is it different than AI, which is a technology which all of us are using as of now. It has become very household thing after the chat GPT was launched. So first of all, what we need to understand is quantum computing is a different paradigm as compared to the classical computing, which means quantum computing and AI cannot be compared because they belong to two different computational paradigms. AI, artificial intelligence, is a very promising technology, but it belongs to the domain of classical computing, while as quantum computing is a new frontier, and it is not only is it different, it's radically different because it does not work in the manner AI or classical computing works. So if you have to see the difference between quantum computing and classical computing, lies in something called the Church-Turing hypothesis. And Church-Turing hypothesis is a theorem which defines what a computer is and what is the promise of the quantum is a computer. So the Church standard Church-Turing thesis, which is applicable to any classical computer, does not fit to the quantum computer because, as I said, quantum computing is a different framework. So if we have to understand quantum computing, we need to extend Church-Turing hypothesis, and that was done by a physicist. His name is David Deutsch. So he came up with something called the Church-Turing-Deutsch hypothesis. And on the next slide, I will tell you why do we need the extension of Church-Turing. So the one of the first things which we need to understand how quantum computing is different from the classical one is in quantum computing, we take information as physical. By that, I mean the way mass or energy or angular momentum or velocity or acceleration or physical quantities, in the same manner, it was realized that information is also physical, which means it like as the way energy follows the laws of thermodynamics or laws of physics. Similarly, information also follows the laws of physics. This particular approach is something which we do not do in classical computing. When we design classical computing, data is not considered something which has to obey laws of physics. But then later on, people, computer scientists and physicists realized that information is very similar to energy or entropy. In fact, entropy and information are very much related to each other. So this realization made people understand that there has to be a different model of doing information processing. And this new model of computation is based on laws of physics. So this is where the difference between classical computing and quantum computing happens, that in quantum computing, in this new paradigm in which information and the data is considered physical. So, and everything which we do with data and information is done as per the laws of physics. So you need a different way of storing the information, and that's where this container comes, which is called the qubit. So qubit is a very, very different kind of a storage system of quantum information. When we say quantum information, by that we mean this is an information which obeys laws of physics. And for that, we cannot store this in the classical bits. We have to find a different way of storing this information. And it's being stored in a system called a qubit. So qubit is an equivalent, quantum equivalent of what we have bit classically. And what happens in this thing is that your information is stored in a physical system, in the two different states of the physical system. I will give two examples. Let's say you have light or you have a supine system. So in light also, you can now store information in light, in particles of the light, which are called the photons. Now, this is very unimaginable from a classical computer science point of view, because classically information is always stored in the 1 and 0 state, which are two states of an PN junction or a transistor. That is how we always believe that the information can be stored in the two states of an electrical system or an electronic system. However, as I told you, the laws of physics allow you to store information in any physical system, which means if we take any physical system, it doesn't have to be an electronic semiconductor system. It can be a magnetic system. It can be an electrical system. It can be a mechanical system. It can be even photonic system. So you can store information anywhere. And the qubit is the system where we store the information. And as I said, one of the examples of the qubit is made out of light. So this is very new way of storing information, where we store information in light, in a magnetic system, we can store in diamonds, we can store in nano devices, we can store it in lots of places. And if you see in terms of data storage capacities, which qubits offer, which quantum computing offers is, you can see the differences between a line and a sphere. When you are on the classical side, your information lies in only two states. Either it can be 0 state or it can be 1 state. But when you go on the quantum side of the information, you have a larger space to store the information and process the information. Because now you have all the states available on a sphere. And it's as you can see when geometrically, sphere is a bigger space as compared to the line. So line is where information is stored classically, even not just 2 points of the line, not every point of the line, only 2 points of the line, which is represented by 0 and 1. Those are the only two states possible where you can store information in a binary way. But on the quantum side, as compared to the classical one, there is a lot more information. So qubit is a bigger space to store the information. So this is one of the promising things which happens in a quantum computer. But this is not the only one. What quantum computing offers you is a new kind of a logic, which is called the quantum logic. And this quantum logic is not what you do classically. It has to be different because, as I told you, quantum computing is a different paradigm of doing computation. It's a totally different way of storing information, different way of processing the information, and different way of implementing the gates on this information. So interestingly, what I want to tell you immediately is this quantum computing logic is inspired by physics, especially the physics of oscillations and the waves. Now, this is really unimaginable because generally when you think of logic, you don't think of oscillations and waves. In fact, whenever we think of logic, we do not think of physics. We think logic and physics are very, very different. But quantum computer is a computing machine in which the logic of this system is derived from the waves and oscillations of a physical system. So this can tell you how weird or how uncanny, how different quantum computing is as compared to the classical computer. So in a quantum computer, the way you can do the logic is like you have 0 state and 1 state, but they can also come together and give rise to something called a superposition. So superposition is a very, very important principle, a logical principle, not the physics principle, but this superposition becomes a logical principle. It allows us to combine 0 and 1 stages. And this is not permissible in classical logic. On a classical computer, you can never bring 0 and 1 together, add them up, and create another logical state. It is not allowed in Boolean logic. But in quantum logic, what happens is that, or on a quantum computer, you can take 0 state and 1 state, in some sense, add them together or superimpose them together and create another logical state. Okay, and this is one of the ways you can see quantum computing is richer. It does operations, logical operations, which you cannot do on a classical side. So as you can see on this block sphere, what you can do is that if you have a qubit, you can do rotations on this block sphere. You can do a lot of things on the logical states on this block sphere. And you can do, as I said, that you can do superposition. But like in waves, once you have superposition, you can also create the phase differences. If you have the phase difference in the waves or the oscillations, it gives rise to the interference. So all these wave-like phenomena, superposition, phase difference, interference, all of these things are known in the domain of physics. But what quantum computing does, it basically takes these interaction phenomena. It basically takes superposition, phase difference, and interference phenomena into the domain of logic. And then it allows us to do more and more things. So here are examples of some of the logic gates, because quantum computer is a computer, and every gate-based computer has the logic gates. So quantum computer also has the logic gates. The only difference is the logic gates are now made up of rotations. So this is also something very different from the classical computing. In classical computing, whenever you have to apply gates, like a flip gate, AND gate, OR gate, XOR gate, NAND gate, they do not do any rotation. They basically do some logical operations. They do some sort of a modular arithmetic, some sort of a binary arithmetic. That's what logic is at the classical level. But what is the logic at quantum level? At the quantum level, logic is not arithmetic. Logic is based on algebra. It's based on rotations. It's based on spheres. So in the quantum logic, there are spheres, qubit spheres, there are rotations, there are angles, there are superpositions, interference phenomena, phase differences, phase angles. So you can see not only does a quantum computer give you more logical space to store information and process it, but it also allows you to do different things which are not possible to be done on a classical computer, which are these logic gates in terms of rotations. Here is a very interesting example. Here is a logic gate, quantum logic gate, which cannot be simulated on a classical computer. It's a very different kind of a logic gate. And you cannot have a head-mod gate on a classical computer, which tells you that on a quantum computer, you can do different kind of logical operations. And what is the role of head-mod gate? Head-mod gate, what it does is that it takes 0, it takes 1, brings them together, and creates an equal superposition between 0 and 1 state. Now, you may ask me, how do I get a sense of what do you mean by creating a superposition? It is in some sense, I am trying to tell you that on a quantum computer, you make a probabilistic mixture of truth state and false state. Let's say you have a statement which has some truth value, then you have maybe the another statement which has a false value, some false value. You can combine these statements together and then add up these truth values. It doesn't have to be 1 and 0. It can be, you can have a statement which has a truth value of 0.5. But this is possible only in quantum computer because we can do mixture of truth value and their false value. Truth state and the false state can be mixed together and we can create these mixtures. So the mixture of these logical states is possible on a quantum computer, and we use Hadamard gate for achieving that. So so Hadamard is basically a superposition gate. It does the superposition for us. Now, if we move on to the next slide, Shane, so I can show you more gates. Now, this is another gate which I want you to think about. So if I tell you that the angles which you learned in your class 10th in trigonometry, or you learned in geometry about the angle, after that you forgot about the angles. They never came in computer science. You think angles have nothing to do with computer science because in computing, we only use binary values, 1 and 0. You add them up, you multiply them, you do arithmetic with those 1 and 0. Angles are not important. So one of the ways to look at quantum computing is that this is a form of computing in which angles become very, very important. I told you the logic gates on a quantum computer are rotations, which means in any rotation, there's an angle involved. So there has to be a logic gate which basically does some sort of angle rotation. And there are some specific gates. They are called the phase gates, which do particular kind of rotations on a qubit. And these gates are not possible to be implemented on classical computer. In fact, one of the ways to understand why quantum computing is powerful is because on a quantum computer, you have phase gates like Z gate, S gate, and T gate. This is one of the reasons which makes quantum computers really, really powerful because these phase gates cannot be implemented on a quantum computer. So if I have to tell you again, what is the difference between the bit and the qubit? In the bit, you can take 1 and 0 values, so you can do bit flip. You can change the 1 and 0, 1 to 0, 0 to 1, or you can do something with this is the bit flip operation. So bit flip operation is possible on the classical level, but on quantum computer, you have bit flip as well as phase flip. So you have more kind of things which you can do with a single qubit using the quantum logic gates. One is the bit flip, as I said, you can do phase flip, and you can do a combination of bit flip and the phase flip. Okay, this extra degree of freedom, this extra power, this extra logical power, this extra computing power, which quantum computer gives us, it makes it more promising and more powerful. So now, but this is not the end of the story. Superposition and phase is not the end of the story. There is one more ingredient, a computational resource. Like as on a classical computer, your computational resource is your memory and the CPU power and the CPU processing time. That is the computational resource which you have. On a quantum computer, you have an external resource, which is called quantum entanglement. And what is the quantum entanglement? So quantum entanglement is this property on a of two quantum of a quantum system, that you can combine two qubits together, and they will get connected in such a manner that the information transfer between them becomes instantaneous. If you have to, if you send some, or if you put some information on one qubit, it is instantly accessible on the another qubit as well. So these two qubits become one single system. They get communicated in a they get entangled with each other. They communicate very closely with each other. Now, this entanglement property is not available on classical computers. So this is another reason why quantum computers are different and they are more powerful, because entanglement, what it allows us to do is that you can have many qubits, you can have hundreds of qubits, and then you can connect them with each other, you can entangle them with each other. Then they become one single system, and you have more better ways and the faster ways of sending the information from one qubit to the another. It's faster. It doesn't have the buffer time, and then it does something more actually. Entanglement. When you have information which is stored between entangled particles or entangled qubits, it is more secure. So this I want to emphasize a little bit. What entangled states offer to us is not just processing speed or the communication speed. It is the security. It is the inherent security which an entangled system has, which is lacking at the classical side. That is why classical computer systems, however fast and robust they are, but they have security problems. They have constant cyber security issues, which is a constant headache on the classical computer system. While as when you go on the quantum computing side, whenever you have these entanglement, when you create the entanglement, you don't just create it for making things faster. You do it because you want to make things more secure. So entanglement, one of the greatest things or greatest gifts of entanglement to the computation is that it gives you ways of doing secure and a faster communication. So this is the another thing which you get on a quantum computing. Okay, the entanglement. I think this is a very well-known property of the entanglement. But as I said, like superposition is not sufficient. Similarly, entanglement is not sufficient. This is not the only thing which you get in quantum computer. There are more things which are called the magic states. They're very, very powerful. They cannot be simulated. You cannot, even the fastest and the greatest classical computer cannot create magic states. So you have some special way of processing information only available on a quantum computer. So if we move on, so now I want to, in the rest of the slides, what I want to do is that, yeah, maybe we can move on, Hussein. I want to quickly jump to quantum machine learning, because that's the topic which we want to talk about. If you Google quantum machine learning, you will find a lot of articles, a lot of news, and a lot of things are already going on quantum machine learning. It is not to say that we will develop quantum machine learning or quantum AI in future. No, it's already available as of now. So now let's ask the question, why do we need quantum machine learning? If we have AI, we have ChatGPT, we have large language models, there's a lot of development going on in AI. Why do we need quantum AI? So let's look at this, what's happening in the current AI domain. First of all, they are very, very expensive. They need a lot of computational power. You need supercomputers, you need GPUs to run AI. And then it also needs a lot of electrical consumption, a lot of power. Then if you keep on going forward, it is not possible to scale this AI infrastructure. And then there are other problems, like as AI models are not, it's not easy for them to deal with the time series data. Then they have a low explainability. Let's say if you have an AI model and if you want to understand what's going on in the AI model, it's not easy to understand it because explainability is very, very less. So because of these problems, and then they are not also eco-friendly, they're not green. And the cost of using AI models, as you can see from this chart, is pretty huge. It's in the billions of dollars. So let's say if a university or if a college wants to develop the models, wants to develop from the scratch AI models, it will not be possible for even governments to develop these AI models because the training of the AI models goes in billions of dollars. So which is very, very expensive for even for governments, even for smaller countries. So therefore, one has to think that somehow what we need to do is that we need to take AI beyond the current state. We need to do somehow make it more explainable, make it eco-friendly, make it energy efficient, make it more efficient, more faster. So you can once again see some of the problems which AI models have. They cannot do very efficient stock market prediction. They cannot do forecasting. It's medical signal production gets very difficult for them. They have optimization problems, and likely or similarly, you can also see for AI models, even if there are sophisticated AI models, they cannot help us to deal with the climate crisis. So that's why these give us the motivation that we need to go beyond current AI models, and we need to enter into the domain of the quantum AI. And over here, you can see we can use quantum computing and machine learning together and create this domain of quantum machine learning, wherein we will use the power of qubits, a larger Hilbert space, we'll use the power of entanglement, we'll use power of the phase gates, we'll power of the magic states. And if you look at quickly, what does QML offer to us immediately? What QML offers to us to doing machine learning, it offers us bigger space, bigger computational space. It offers us parallel computation. It offers us physics-based interpretation. If you build a quantum circuit-based machine learning model, it's more easier to interpret it and understand it, what's going on. It's based on the physics-based principles. It also incorporates from physics, it incorporates dynamics into the machine learning model, which is not possible classically. It's not like this black box model. It has more clarity. Similarly, it's not hungry for energy, and you can do better optimization. So all of these things together make us or motivate us that we should be going for the quantum machine learning. And here is something which you can offer. You will see if classically you have a exponential problem. If you do the same problem classically, it makes this problem softer, and you can do it at a faster scale. Okay, so to the next slide. Okay, so and as I said, a lot of data in the world is time series data. It is not, as of now, AI is doing great if you have images, if you have text, or if you have some numerical data. AI models do great on these things. But however, as I said earlier, whenever you have a time series data, which is like ECG, you have ECGs, you have financial stock markets, or you have some financial data, which is time series data, or you have climate change, weather forecasting. All of these problems, that's where AI struggles. And this is where we can start building quantum AI models in all those places, and especially also in the language also. Classical large language models do not understand language fully. Then there is this domain we were talking about, that what quantum can offer to us is a bigger feature space. Whenever you use kernel methods in classical machine learning, you need a large feature space. It's like you take data and map this data to the higher dimensional feature space, and then solve the problem in the feature space. As I told you, what quantum computing does, qubits will allow you, they will allow you to this larger feature space. So you can take your data, map it to the larger Hilbert space or quantum space, and thereby you can build more efficient kernel models. So this is one of the domains where quantum computing can offer better machine learning models, is the quantum kernel models. And as I said, one of the reasons why kernel models, or we can build better quantum kernel models, is because that you can get a bigger feature space on a quantum computer. So now moving on. And as I said, in quantum machine learning also, you can benefit from these lots of logical operations, not just space alone, but you can also benefit from these new gates which are available from, as I said, there is phase flip. There are extra degrees of freedom available for us for encoding our data into a machine learning model. So, okay, moving on. Okay, so but what is quantum machine learning? How do you understand it? So basically, what do we do? How do we develop a quantum machine learning model? Those of you who are familiar with data science, you would remember in a data machine learning model, what happens is that you have data which gets pre-processed, then it gets into the machine learning model or a deep learning model, which does further processing of the data, applies a linear regression or kernel method or random forest or any deep learning model. In a quantum machine learning model, the extra thing which you do is we also have you have a neural network involved, but you also have a quantum circuit involved. So first the data it goes maybe first into the quantum circuit, gets encoded into the qubits. And after that, we do certain processes into the quantum circuit. After that, we do a measurement. It goes back to the classical data. This classical data goes through a machine learning model. So you have a quantum component, that you have a machine learning component, then you do those things. And whenever you do extra quantum circuit layer in front of a machine learning model, what we have found out that you not only get many times you get better accuracy, but most often what happens is that you can solve a problem which generally is difficult for machine learning model, classical machine learning model to solve. So this is a, in a some sense, a cartoon picture, a sketch of how a quantum machine learning model looks like. How is the structure? So you once again do optimization and all that, but you also have the extra quantum layer and you have variational, something called a variational quantum circuit. So you build it the same way, you have a machine learning model. It is just that now this machine learning model is working on a quantum circuit. So you do rest of optimization, parameter optimization, all the things, gradient descent, all those things happen classically, but then you have an extra layer. Okay, so this is the basically the sketch of how a quantum machine. In CQI, the company which we run, these are some focus area which I want to talk about quickly. So there is something called the quantum reservoir computing, quantum natural language processing, quantum optimization, and quantum neural network is a broader area. So talking about these two, right? Quantum reservoir computing is a specific method of a quantum, it's a quantum machine learning domain. But what it does is that it's a very nice method to deal with time series data. So this is what one of the areas which we are working on. Then there is something called a quantum natural language processing. Okay, and as I said, this QNLP is also one of the good applications which brings quantum power to language processing. Now, in quantum reservoir computing, what do we do is that this is another difference between classical machine learning and quantum machine learning is in the quantum machine learning, you have the dynamics, physics-based model. What it does dynamics. Dynamics means it allows you to change the data in time. You know, it allows you to understand that temporal changes, what happens to the data. If some data is changing with time, how does that change happen? Uh, uh, you can use dynamics of physics to understand that temporal data. So this is why reservoir computing or dynamics-based computation is something which is beyond classical AI, because classical AI does not have dynamics-based computation. It only happens in a quantum computing setup. Okay. Yeah, moving on. Okay. Now, this is one of the important applications of quantum computing to machine learning is building something called a reservoir. And reservoir is not very similar to standard machine learning models. As I told you, the reservoir is a machine learning model, but it has been designed to deal with time series data. Okay, and it is different than that. You would not have seen a model or an architecture like this in classical machine learning, because what it does is that it takes input layer. And here is a good example of a quantum reservoir computer. So what you see on your screen is you have those gates, these colored gates. So these are the quantum gates. The data comes in, and these 000, what you see, these are the different qubits which you have over there. Time series data goes, it gets loaded into the qubits, it gets initialization, then it's sent to the quantum circuit. In the quantum circuit, it's being loaded to these various gates. Every gate has some values, which are these angles, and you can put them there and you can encode your data. After that, you can see this, the U layer is there. So this is all happening on a quantum computer. Once you get this whole thing done on a quantum computer, then it's being passed on to the machine learning, classical machine learning model, let's say regression or a classification. And this is how you do a machine learning task using a quantum circuit as well. And as you would expect to from the power of quantum computing, you do things better way, you do things in a more powerful manner, in a more efficient manner. And this is one of the, as I said, one of the important applications of quantum computing to machine learning, because with the quantum reservoir computing, we have a better way. Something which AI cannot do easily is this way of quantum reservoir computing for time series data. So we do it in a much better way if you use quantum computing. So yeah, okay, we move to the next slide. Okay, here what we use something called a mid-circuit measurement, and mid-circuit measurement is this nice mixture of using measurements. And what is a measurement? Measurement is basically reading out the quantum information. Let's say you have information in a quantum circuit. Whenever you read that information, it gets transferred from classical quantum to classical. This has got a measurement operation. Now, generally, measurements are at the end of the quantum circuit, but that's not how it should be. We need measurements at every place of the quantum circuit, and mid circuit is that technology which allows us to do measurements anywhere in the quantum circuit. And once you do that, you can pass the information to the classical machine learning model. And it's a very sophisticated thing as of now, which we do, this mid-circuit measurement, and we have to use it in the quantum reservoir computing. Okay, so next slide. Okay, now I want to talk to you about this important thing about dynamic circuits. I have been talking about quantum circuits, and quantum circuit is essentially a version in which you use qubits. On the qubits, you apply quantum gates, and you get a quantum circuit. But many times in quantum computing or quantum machine learning, what you need to do is that you want to apply the classical control logic, like if gates or while loop, for loop, or these conditional logic gates, conditional logic, which we use in programming languages like Python. Many times you or any programming language, you use for loops, while loops, or if else conditions. So many times we need these conditions to be applied on a quantum circuit as well. So dynamic circuit is this mechanism within which you apply classical logic inside a quantum circuit. And now you can imagine you have a very, very interesting situation that you have classical control conditions like if else condition or for loop or while loop sitting inside a quantum circuit. And it makes this circuit very, very different from the classical standard, because if you have a standard quantum circuit, you can only do quantum logic in that. But in a dynamic circuit, you can bring classical control things, control conditions inside a quantum circuit. That's why it becomes dynamic, because you can use classical logic processing or classical if-else conditions to process the information or to tell a quantum gate what it has to do. So it gives you some control on the quantum logic gates, but from the classical programming side. That's why dynamic circuit is one of the very, very sophisticated technologies which we can use in quantum machine learning. And such a thing does not happen on a classical machine learning, because dynamic circuit has a quantum component. Now imagine a situation where you have this dynamic circuit and you are using it for solving a machine learning problem. You can see that it is going to be very, very powerful. So this is what we do. If you go to the next slide, this is what we do for our reservoir quantum computing. So we bring it together and we are able to deliver a very, very powerful architecture for quantum reservoir computing. And what it does for us is it allows us to solve some of the important problems in finance, some of the problems in logistics and supply chain, in the energy domain, and also in the life sciences, because life science is a very, very complicated, or healthcare is a very complicated domain. It is very tricky to get the data from humans and then deal with that data. It has a lot of fluctuations and all that, but it's also simultaneously a time series data. As I gave you an example, if you have a patient, you can take an ECG of that patient. Or for example, if you look at your heart activity, this heart activity, the heartbeat which happens, it happens with time. That's how we measure heartbeats. We measure it in time. So if we want to understand whether our heart, whether our cardiovascular activity is normal or it is not, you have to have a way of dealing with this time series data. And as I told you, if you use even the sophisticated AI models to understand the cardiovascular activity or cardiac problems of a human being, it's not possible. It wouldn't be possible entirely, because our heart generates time series data. Our heart is an oscillator. It's a non-linear oscillator which keeps on generating time series data. And you need a model which can do time series processing for this cardiac data. And as I told you, so this quantum reservoir computing is one of the terrific applications of bringing quantum and AI together and solving some of the problems which we have in healthcare or cardiovascular. It's very common nowadays to get heart attacks. So you can detect heart attacks if you have a quantum machine learning models. So I think that is where I would like to stop, maybe for some questions or some discussion. I wanted to give you a kind of a sneak peek about what can we do and how can we bring these two very, very important technologies of our time, which is artificial intelligence or machine learning and deep learning, combine it with quantum computing. So I would be very happy. I know for many of you, it may be very new, quantum computing, listening about quantum computing and understanding what the power is. So I wanted to give you some sense how is quantum computing different? How is fundamentally in terms of qubits, in terms of quantum logic, in terms of superposition, entanglement, and other things, and how you can take this power of quantum computing to solve some of the pressing problems of our time. So I would like to stop here. Please ask me questions. If there are any confusions, questions, I would like to answer them.
Good evening, sir.
Yes.
Sir, you said measurement is possible in quantum communication. So what are the advantages of mid measurement?
Okay, sure. So one of the advantages is it is called quantum error correction. So unlike classical computer, in a quantum computer, what you need to do is that you need to build a quantum computer, and so that your quantum circuit works properly, you have to do error correction. Because whenever you run a quantum algorithm, the qubits are very fragile. If you have an electric pulse or electromagnetic signal going on, it can disturb a qubit. It can also disturb a quantum gate. So therefore, what we need to make sure on a quantum computer is that whenever you run a quantum algorithm or a quantum circuit, error correction is also being done. If there are some errors, those errors have been corrected before we get the final results. So mid-circuit measurement is needed for doing that quantum error correction. This is one of the applications. But even in machine learning, this is in error correction domain, but if you take in machine learning or optimization or finance, you need to read, you need to intervene or disturb your quantum circuit and extract the data in between, read that data. So it gives us better control on our quantum circuit. So you can disturb it in anywhere in the quantum circuit. So it gives us more allows us to make more robust and better algorithms and applications dealing with, especially with the time series data, in addition to the quantum error correction.
Okay, sir. Thank you so much.
Hello.
Yes.
Sir, you said QML and QRC are deliverable in life science. Can you explain with one example how they are contributing in life science?
Yes. So I talked about, let us say we have this problem, which is I think it's very prevalent in India, is detection of potential heart attacks. There's a patient who is going to has a BP problems, and now this patient is on the verge of getting a cardiac arrest or something happens to his heart. So, but generally you will see people get cardiac arrests, then we take them to the hospital and then we kind of treat them. But it would be nice before somebody gets a cardiac arrest, we have some way of detecting it. Now, why does not it generally happen? Because cardiac arrest or a cardiac activity is a dynamic thing. Your heart beats in time. It continuously has variations with time. In the morning, you will see there is one BP. In the evening, there is another BP. Something happens in the family or something happens in the life, the BP changes. So, but it changes with time. Now, understanding these BP changes or heart changes, what happens to the heart in time is generally a difficult problem for AI. Because as I told you, AI is not good in solving AI problems, in solving time series problems. So in healthcare, what we can do, we can build based on the QRC, we can take this patient data, this streaming data, or we can take a patient, any patient where we have some sense that this patient may potentially get a heart cardiac arrest. We can feed that data to the QRC, and it will give us some sense already that this person is going to get a cardiac arrest. In that way, it can play a very, very important role in, at least if not diagnosing exactly or detecting exactly, at least giving us some some detection mechanism, some alarm beforehand, so that we can monitor that person closely. This is one of the least examples. I will tell you something more. There is a famous hospital in USA. It's called Cleveland Clinic. So they are one of the first hospitals in the world who have adopted quantum machine learning for healthcare problems, for diagnosis, for something called a precision medicine. Because if you see, whenever there a problem arises, in machine learning language, it is called anomaly detection. So to diagnose problems in patients is basically you have to build a system which can do anomaly detection. The only challenge is that this anomaly detection has to happen in a time series data. which is a little challenging problem for AI. But you can bring quantum ML and quantum reservoir computing, especially to do this anomaly detection in time series data. And if you do so, you will be doing a great job and helping the patients. In that sense, this is one simple example, but I think you can read more from Cleveland Clinic. How are they using quantum AI for patients and healthcare?
So it is like, sir, prediction model sort of.
Yes, it is. It's a predictive model for time series data, especially.
Okay, okay. Thank you, sir. Thank you.
Pleasure.
Hello, sir. This is Ashish Onmai, and I have
Yes,
one
Jason.
very generic query. Nowadays, there is a boom of ChatGPT, Gemini, and many other such AI models. So, when can we see such quantum models coming into market, which can help users, a large number of users, to address day-to-day problems or search, etc.?
Okay. So, Professor Ashish, thanks for asking that question. It's a very important one. But before that, I think I want to repeat the name of the hospital is Cleveland Clinic. It's like a very famous hospital in USA. Like there is another hospital called Mayo Clinic. Similarly, there is this Cleveland Clinic. If you write quantum computer in healthcare, you will find Cleveland Clinic anyways in USA. So now the question is, like as people are nowadays using chat gpt, even students, everybody is using chat gpt. Question which Professor Ashish is asking, when will something like this happen? So I want to tell you, it may occur to you, because you may not, all of you may not be working in the quantum industry like me. You may be waiting, okay, someday this quantum computing will come and it's in future. I want to today, by this talk, I want to send this message to you. Quantum computing is happening now. When I was with IBM 4 years back, we were working with the clients where we were developing quantum computing applications for finance, for optimization, for energy, for healthcare, for banks. Almost all the banks, like as HSBC, JP Morgan, or other well-known Citibank, or any well-known American bank, American Express, all those banks are already using they are already using quantum computing or quantum machine learning for their financial applications. So it has not become, I mean, maybe in few years, I believe my own understanding is that within next 3 years, quantum computing is going to become more public, because in 3 years, what is going to happen, the current security, like is whether it's in a website or even quantum computer, you or your classical computer, you always use some security system. Okay, these security systems are believed to break down by 2030. So when these systems will start breaking down, the public will come to know. They will come to know something is going on with my website, is something is going on in my in my computer, in my local machine. They will get to know that there is a need for something more, which is quantum. So I think we just have to wait next couple of years. By 2028 or maximum by 2030, everybody has to switch at least to some form of quantum computing. Okay, especially in the domain of security, and especially in the domain of time series, whether it is finance, whether it is medical data, whether it's weather forecast, whether it is climate change, any domain which involves time variable, which involves dynamic change, will have to use quantum computer sooner or later. So let's wait for a couple more years, and we will have a chat GPT like moment in quantum computing.
One more question, sir. Do we
Yes.
have any platforms available where people can experiment with quantum machine learning?
Yes, obviously. Yeah, there are. One of them is called a Qiskit. Maybe Hussein, if you write, Hussein can write. There is one thing called a Qiskit, which is from IBM. Then there is something called a Penny Lane, which is from Xanadu, a startup in Canada. Then in Amazon also, the standard Amazon, where from we get books and other groceries and other things. They also have they also give you a platform. It's called Amazon Bracket. So Amazon, the standard Amazon, they also have a quantum computing facilities. In the sense, you can get on Amazon and go for Amazon Bracket, and then you can start working with quantum computers. So Amazon is there, Amazon Bracket is there, Qiskit is there, Penny Lane is there. Then Microsoft, Google has Cirq, Microsoft also have some, I think they call it Q hash or something. So in all of these places, you have these platforms available. And I would suggest and recommend all of you start playing with quantum platforms. Do not wait that one fine day in 10 years or 3 years or 5 years, quantum computer will come to you. They are already there. It is just that you are not using the power of quantum computing. And there is already quantum cloud. Quantum computing is already available on cloud, like is IBM cloud, Google cloud, or I think maybe Microsoft also has something, Amazon also, as I told you. All of these cloud platforms have quantum computing platforms available. Similarly, in the security domain, you will see WhatsApp has end-to-end encryption, but there are messengers like, I believe, Telegram or Signal. Signal, I believe, has already started this quantum encryption. It's called a post-quantum cryptography. It has already been started integrating into lots of messengers. So within 2 to 3 years, you will see quantum coming in, quantum security, especially post-quantum cryptography. Everybody has to use it into 2 to 3 years, and we will not have a choice. In the way we did not have a choice to use Chat GPT, we have to use it. So I would suggest we start exploring post-quantum cryptography platforms, or these Penny Lane, Google, or other kinds of things, or starting from today. I think my session will be successful if you guys can start, all of you start exploring them. Then I will feel good that I have been able to connect to you with the practical platforms and important areas in quantum computing.
Yeah, thank you, sir.
Thanks.
Any more
And by
questions,
the way, if
participant?
yes,
Kanchan, madam,
Yes, ma'am.
if no questions are there, please conclude the session.
Yeah, ma'am. So, on behalf of the organizing team, I extend our sincere and heartfelt thanks to our esteemed resource person, Dr. Ruksan Al Haq, for delivering an enlightening and impactful talk on quantum AI and its applications. The session was rich in content and provided valuable insights into the emerging convergence of quantum computing and artificial intelligence. Sir explains us the difference between the classical computing and quantum computing, the various gates used in quantum computing like poly gates, Hadamard gate, phase gates. Quantum gates have striking differences from the classical one. They are reversible, they can create superposition and entanglement, and there are infinitely many possible single qubit gates. Sir discuss the current states of AI. Sir, talk about the quantum neural network, quantum supervisor computing, quantum natural language processing, and quantum optimization. Also, he discussed the mid-circuit measurement in QRC. Sir, we truly appreciate the depth of the knowledge and engaging interaction that made the session highly informative and inspiring. A special word of appreciation goes to all the participants for your active involvement, enthusiasm, and thoughtful interaction, which truly added value to the program. I thank everyone present here for their time, cooperation, and support. We hope that the knowledge and insights gained during this FDP will be beneficial in our academic and professional endeavors. With this, I conclude the vote of thanks. I request all the participants to kindly turn on their camera so that we can have the photograph. After that, you can fill the feedback form for the day 5.
Okay, one more announcement, all the participants. Tomorrow our session will start at 2 p.m. So you all kindly join it on time.
Madam, exam at what time?
Hello, yes?
Ma'am is asking about the exam time, ma'am.
Exam time after third session, madam. Validity function will be there, and after that, exam will be there.
And also it will be on portal,
ATAL portal.
ATAL portal.
Tomorrow we will declare the
Yes.
time at what time we will upload the questionnaire on ATAL portal.
Okay, madam, because as usual, we are having Saturday also office work. College is
Okay.
there, so that's why
Yeah.
after 4:35 means it will be no problem for us. Otherwise, I will adjust some my classwork and I'll attend the exam.
Madam, tomorrow 2 p.m. to 6:30 p.m. we are having 3 sessions. After that, we are
Okay,
having
okay.
validatory function, and then quiz will be there. So
Thank
easily
you,
you can
thank you, ma'am.
attend. There is no problem.
Thank you.
One more thing, the quiz will be on the ATAL portal, and once the quiz is out, it will be only there for 1 hour. Okay, so all the participants need to attend and complete the quiz in that 1 hour only. Otherwise, if you miss out, you will not get a certification from the ATAL. Okay, so please be there on time and complete your quiz in that 1 hour. Okay, once the quiz is closed, it cannot be reopened, so you may miss out the chance for your certification. Okay. Yeah, thank you everyone for turning on your cameras.
One thing I would like to discuss with all of you that we should have a 3 hours to 5 days, 15 hours training session. It should not be it becomes too hectic. Quality is more important than quantity. So I request all the professors to come forward and give the feedback on the ATAL portal like that also. If you agree with this point, that is your choice. Thank you all. Good night.
Yeah, actually, ma'am, we have a restriction from ATAL that we need to have minimum 13 sessions. So we can't help in that. It is a decision to be taken by ATAL.
Yeah, 13 session and each session is of 1.5 hour. So it's a there
There
norms.
is
These
no
are the conditions by
separate
ATAL only. Yeah.
this answer in one of the point where they have asked for email address or something like that. There I have attacked this point also, comment on it.
Sure, madam, you can do.
Yeah, thank you everyone. This is the end of the day for today. And tomorrow will be our last day. So hope everyone will be there on time and complete all the activities in time. Thank you and good night.